We're still dealing with linear differential equations with constant coefficients. So far we have dealt with equations where the right-hand side was equal to 0. So now we turn our attention to a more general case, and I've given an example here to solve the differential equation d2y dx squared plus 3dy dx plus 4y equals 3x. So the right-hand side now has a function of x. It is no longer 0. Now, part of this process is to find what we call a particular solution, which from now on we will usually call the particular integral for the equation. Right, for this particular episode, we'll concentrate solely on finding a particular integral, not on the general solution for the entire equation. Okay, so the process here is to look at what the right-hand side looks like and try a solution which resembles it. Now, the most general form of the right-hand side would be ax plus b. So we'll try y equals ax plus b. Okay? So, and then differentiating, we get dy dx equals a, and d2y dx squared is 0. And substituting back into the original equation, over here, we'll get 0 plus 3a plus 4ax plus 4b has to be identical to 3x. In which case, equating coefficients, 4a will equal 3, which means a is 3/4, and then also 3a plus 4b has to be 0, so 4b will equal minus 3 times 3/4, which is minus 9/4, and so b will be minus 9/16. And the particular integral will be this expression here, 3/4 x minus 9/16. Now, notice that this has no arbitrary constant. That is why it's called a particular solution. Example number 2, d2y dx squared plus 5dy dx plus 2y equals e to the power 2x. So again, we'll try a solution which resembles the right-hand side, and the simplest one obviously is to try y equals a e to the 2x, where we've got to try and determine where a is if a in fact exists. So dy dx will be 2a to the 2x, and d2y dx squared will be 4a to the 2x. And substituting back into the original equation will give us 4e to the 2x plus 10a e to the 2x plus 2a e to the 2x equals e to the 2x. Adding everything up on the left-hand side, we'll get 16a e to the 2x equals e to the 2x. And so quite easily 16a is 1 and a is 1/16. So our particular integral in this particular case will be 1/16 e to the 2x. We could say that y equals 1/16 e to the 2x is a particular solution of the equation. Note again that there is no arbitrary constant. For the third example, we need to find the particular integral for the equation d2y dx squared plus dy dx plus y equals sine x. This time, we'll let the right-hand side, or try the solution y equals a sine x plus b cos x. And this is a generalized form of sine x plus 0 cos x. Remember, sine x and cos x are closely related, so it was quite reasonable to assume that part of the solution might have a cosine part to it. Okay, well, differentiating, dy dx equals a cos x minus b sine x, and d2y dx squared is minus a sine x minus b cos x. And substituting back as before, we'll get this rather long expression here, minus a sine x minus b cos x plus a cos x minus b sine x plus a sine x plus b cos x, and that's got to be identical to the original right-hand side, which was sine x. Simplifying, we get a cos x minus b sine x is identical to sine x. So here, there's no cos x on the right-hand side, so a is 0, and b is minus 1, and our particular integral is y equal minus cos x. Right. So those are 3 examples to get us started. Some particular integrals are much more complicated, but obviously at this stage we don't want to introduce that. We want to get you slowly into understanding the process and gradually, bit by bit, make it harder. But I've given you 3 examples for practice, which are pretty well on the same lines as what I've illustrated above. And here are 3 of them, and I've given the solutions on the right, but have a go at them before looking at the solutions. I'll just give you a minute or 2 to copy them down if you so wish. So we'll end it there, and thank you for listening.